After many years of mathematical research, I am glad to finally present the first edition of my new book, Introduction to Topographical Spacetimes Theory, a fascinating mathematical journey into the geometric foundations of reality. In this short video, I'll present the main ideas behind this exciting topic, and I hope you'll find it intriguing enough to want to learn more. So without further ado, let's dive right in. Topographical spacetimes theory, TST for short, is both an intriguing, purely geometric model and a fundamental framework for understanding our physical reality. As such, it should captivate mathematicians and physicists alike. TST brings remarkable clarity and simplicity to scientific discourse and enhances our understanding of reality's geometric underpinnings. The book aims to introduce TST and convince you of two key points. 1. Reality is best modeled using topographical spacetimes. 2. Any mathematical model of reality that assumes the existence of physical entities other than topographical spacetimes is either emergent, i.e. not fundamental, or incorrect. Consequently, without TST, one's comprehension of both geometry and physics remains incomplete. If, upon reading this book, you find these claims compelling, then it will have achieved its purpose. The term topographic derives from two Greek words, topos, meaning place, and graphein, meaning to write or to draw. Together, these roots form a word that essentially means to describe a place. In modern usage, topographic primarily relates to the detailed mapping or study of surface features. It is frequently associated with topographic maps, which depict elevation changes using contour lines. Drawing inspiration from this profound Greek etymology, TST introduces the concept of a topographical space. This can be understood as an elevated space, essentially an embedded space that can be described by elevation functions, as illustrated in this example. So, at its basic level, the idea of a topographical space is very intuitive and easy to understand. Let's take a closer look at the mathematical structure of the following simple topographical space. This two-dimensional surface can be generated by drawing the graph of a real function t of two variables x and y. We can think of such a function as an elevation function. This function, true to its name, specifies the height of the surface at each point relative to some base space. We'll refer to this elevation function as the topography of this 2D space. It is quite obvious to see that the topography of a topographical space completely determines its geometry. To facilitate our discussion of topographical spaces, let's introduce some useful terminology. We'll refer to the x and y directions as physical dimensions, and the z direction as a topographical dimension. Using this convention, we can say that this topographical space has two physical dimensions and one topographical dimension. It can denote this as a 2-to-1 topographical space, defined by a 2-to-1 topography. Additionally, we observe that this 2-to-1 topographical space is embedded within a 2+1 dimensional linear vector space. We'll refer to this vector space as the hosting vector space. So we can now say that we are looking here at a 2-to-1 topographical space, defined by a 2-to-1 topography, and hence is embedded inside a 2+1 dimensional hosting vector space that has two physical dimensions and one topographical dimension. We need not confine our imagination to a single topographical dimension. In fact, we can easily conceptualize and draw the following 1-to-2 topographical space. In this example, we have one physical dimension x and two topographical dimensions y and z. Consequently, the topography of this embedded one-dimensional space, i.e. a curve, is defined by two elevation functions, ty and tz. Generalizing this concept, we can say that an NP to NT topographical space is an NP dimensional space embedded within an NP plus NT dimensional hosting vector space. This embedding is achieved through NT topographical dimensions and elevation functions, which collectively define the space topography. It's important to note that regardless of the number of extra topographical dimensions NT, the intrinsic dimensionality of a topographical space remains fixed by its number of physical dimensions, NP. It is easy to understand that as the number of topographical dimensions increases, the potential geometric complexity of the resulting embedded topographical space grows. Each additional topographical dimension introduces a new degree of freedom for the embedded space to twist and turn within the hosting vector space. If we adopt the term emergent physics to describe these various twists and turns of a topographical space, we can assert the following principle. The greater the number of topographical dimensions a space possesses, the richer its emergent physics can become. This principle concisely captures the relationship between the topographic dimensionality and the potential physical richness of topographical spaces. Another intriguing observation emerges from our discussion. Given that the geometry of a topographical space is entirely determined by its topography, we can readily conclude that the metric tensor of such spaces completely emerges from their topography. This leads us to a significant insight. The topography of a space is more fundamental than its metric tensor. This realization naturally brings to mind Einstein's theory of general relativity, which is fully described by the metric tensor of spacetime. Connecting these concepts, we're led to an enticing question. Could a more fundamental formulation of physics be possible if we were to take the topography of spacetime as our starting point, rather than its metric? This line of inquiry welcomes us to the realm of topographical spacetimes theory. The following figure illustrates the contrast between a metric-based spacetime and topography-based spacetime. As depicted in the left-hand diagram, basing spacetime geometry solely on a metric tensor leaves charge-related and quantum phenomena without a clear origin. Consequently, their connection to spacetime geometry remains unknown. In contrast, the right-hand diagram suggests that a topography-based spacetime offers a more comprehensive and unified geometric picture. This approach leads to a profound proposition. All physical phenomena emerge from spacetime's topography, and hence there is nothing in spacetime but spacetime itself. This is a bold claim, and the primary aim of the book is to provide evidence supporting it. Now, we already know that a spacetime has 4 physical dimensions, so for topographical spacetimes we can set NP equals 4. We also know that the higher the number of topographical dimensions a spacetime has, the richer its emergent physics can be. And so, the question arises regarding the minimum number of topographical dimensions a spacetime must have in order to be able to account for the physical reality we observe. The answer that TST gives to this question is 4 to the third topographical dimensions. Hence, in TST, spacetimes are taken to be 4 to the third topographical spaces embedded inside a 4 plus 4 to the third dimensional hosting vector space. It's interesting to note that other models employing extra dimensions, such as string theory and Kaluza-Klein theory, run into so-called compactification issues, which arise from the need to somehow get rid of these extra dimensions. Contrary to that, TST defines spacetime as 4-dimensional, and thus avoids the need for compactification in the first place. In TST, the additional topographical dimensions are not integral parts of the spacetime itself. Rather, they serve to describe how the 4-dimensional topographical spacetime is embedded within a higher dimensional hosting vector space. This fundamental distinction elegantly sidesteps the compactification issues that plague other theories. This straightforward approach to dimensionality in TST offers a significant advantage in terms of conceptual clarity and mathematical simplicity. Now we know that a topographical spacetime requires 4 to the third elevation functions to fully describe its embedding within the hosting vector space. Interestingly, it proves tremendously advantageous to arrange these 4 to the third elevation functions in a 4x4 matrix of quaternions. To distinguish them from real numbers, quaternions are decorated in TST with an upper double wave. A quaternion, by definition, consists of 4 real numbers. Consequently, a 4x4 matrix of quaternions provides us with exactly 4 to the third real numbers. This elegant arrangement leads us to a crucial conclusion. The entire geometry of a topographical spacetime can be completely determined by a 4x4 quaternion matrix topography. This compact representation of spacetime topography not only captures the full complexity of its geometric structure, but also offers significant mathematical benefits in describing and analyzing such topographical spacetimes. As an example of the importance of this representation of the topography of a spacetime, I quote here without proof 2 of the most major results of TST. First equation expresses the gravitational field of a spacetime as a function of its topography, and the second equation does the same thing for all charge-related fields, including electric, weak, and strong fields. So together, these 2 equations show us how all physical fields emerge quite simply from spacetime topography. The full derivation and meaning of these equations can be found in the book. Finally, we notice that, much like Hilbert's Grand Hotel, the hosting vector space has the capacity to simultaneously accommodate an infinite number of embedded topographical spacetimes. We can depict it using the following diagram. The horizontal axis represents all the physical dimensions, whereas the vertical axis represents all the topographical dimensions. Each curve in this diagram represents a different topographical spacetime embedded inside the hosting vector space. The fact that we can easily embed infinitely many topographical spacetimes within the hosting vector space opens the door to a much more mathematically rigorous development of the idea of the many worlds interpretation of quantum theory. This is why the word spacetimes, in plural, appears in the name of the theory. It's because in TST we are interested in studying infinite sets of embedded topographical spacetimes. Furthermore, since the topography of each spacetime is fully represented by quaternions, we can scale each topography by a different complex number. This complex scaling of spacetime topography leads to the idea of topographical proportions. If we plug the scaled topography in the equation for the gravitational and charge-related fields, we notice that these physical fields are scaled by the square norm of the complex number. This allows us to compute the expected value of these physical fields in exactly the same way it's done in quantum field theory. It's remarkable how effortlessly and naturally complex numbers and quaternions emerge within the framework of topographical spacetimes. The introduction of quaternionic topography unlocks a realm of powerful geometric manipulations. These manipulations, arising from multiplication of the topography by complex numbers, give birth to the central concept of topographical proportions, from which quantum field theory eventually emerges. Thus, TST reduces the entirety of physics to pure differential geometry. More specifically, to the differential geometry of embedded topographical spacetimes. This elegant reduction offers a unified mathematical framework for understanding the fundamental geometric nature of our universe. For additional information, you can buy the book at Amazon.com, subscribe to my YouTube channel, visit my Facebook page, and join my Facebook group. If you like this video, don't forget to like, share, and subscribe. Thanks for watching.